So I'm going to redraw that vector. I'm going to put it here, 10 meters per second. I'm going to draw the components. And this is going to be v1x, and this is going to be v1y. And this is my 36.9 degrees. Now I happen to know to find Vx if you do your trigonometry, and I'm not going to do the math here, you should be able to do it. But if you take the cosine of 36.9 degrees with 10 being the hypotenuse, 36.9 degrees makes a 3, 4, 5 triangle. So if I see 36.9 degrees or 53.1 degree, that's a 3, 4, 5 triangle. And if I do that correctly, I'm going to realize that this particular x velocity here, that should be worth 8. And if that launch velocity is worth 8, then this y velocity should be worth 6. So again, I said launch, this is the x velocity. So as this thing is traveling, it's moving 8 meters a second in the x direction, and it's initially given 6 meters per second upward. Then, so that's important. The other thing I want to know is, okay, well, if I have this initial information about the velocity and I broke the motion of the initial velocity of the components, well, what am I being asked and where am I going? So let's ask the following questions first and foremost. Let's ask, what's the range? That's delta x. And let's ask hang time. And that's going to be your delta t. And in order to answer that, I need to know along this pathway, where do I start and where do I end? So I'm going to go from point A, obviously that's my initial position, my launch. And in order to find range, I need to go all the way to here. I need to go to point B. So I'm going to analyze this from point A to point B. And when I do that, I need to list what information I know and list what information I'm looking for. And in the x direction, I have some information. In the x direction, I know that I'm moving at 8 meters a second. So here, x direction, velocity 1x equals 8.0 meters per second. And so that's good to know. But otherwise, that's all I know. I mean, I'm looking for this delta x, which is going from A to B. I don't know what that is. And I don't know what the time in the air is. I don't know. In the y direction, I know a little bit more information, believe it or not. In the y direction, I know that at the very beginning of the launch, I'm moving at 6.0 meters a second upward. And that's going to help me. So we know, well, the other thing we do know in the y direction is once it's launched, as we saw in the previous video with the launch, it's in free fall, right? It's as if it's just moving up and down without sideways motion. So this is launched upward at 6 meters a second. It's going to undergo the acceleration due to gravity. So it's going to go up, slow down, stop, and come back down again. And so let's approach that y direction as if it were just a linear acceleration problem due to free fall. And so I don't know what delta y is. I don't know how high this is going to go. Actually I do. We'll get to that in a second. V1y equals 6 meters per second upward. make that positive because direction matters here. V2 in the y direction, we'll talk about. We know that it's in free fall, so it's negative 8.1 meters per second squared. And again, I don't know what the time is. Now, what we have to understand is, as this particular projectile moves through the air, the x speed, no matter where I'm at, is always going to remain consistent. We saw that with the cart. The y speed in every position is going to get lower to nothing, and it's going to get faster downward, and then even faster downward. And again, this vector could be rewritten here, showing the x and y component at this position, but remember, I had to add it head to tail to actually get that that resulting starting that starting vector. But if this thing is traveling through the air and comes all the way over here, I know some things, even though I didn't have to do any math. Firstly, I know the delta y, because if I'm launched from the ground and then I'm about to hit the ground, how much up and down happened? Well, yeah, it went up, but then it came back down. So the change in y, the displacement in the y direction, is nothing. Because remember, displacement is final minus initial. Well, final, I'm on the ground, initial, I'm on the ground. Yeah, stuff happened in between, but displacement doesn't care. The other thing I do know is my final velocity in the y direction. Because if I launch this at 6 upward from this spot, and it goes up and comes back down to the same exact height because of the symmetry of free fall. So if I throw it up at 6 and catch, that's terrible. But if I throw it up at 6 and catch it right, it's got to be at the same height though. It's going to be coming down with 6. So I do know the y velocity right here, except it's downward. Now this only works, of course, if it's launched and lands at the same height. If the landing point is a different height than the starting point, then that's not true. Things are going to change. The time, I don't know. I don't know the hang time in the air. Well, I know x information, I know y information. Now that I know that information, I should be able to figure some things out. And the question is, well, which direction is the x direction information or the y direction information? Which direction has information that I can use? Because typically that's what happens. One of the directions you have enough information to use, and the other direction you don't. All right. Well, let's look at this. I want to know the hang time, I want to know the range. Well, the range is delta x. Well, I don't know time. I do know velocity, but I don't have enough information here. I need the time, which is the hang time. Okay, well, let's go to the y direction. I have lots of information in the y direction. So we need an analysis that's going to get me time. And there's a bunch of different formulas that you can actually use here, but I'm going to go for the simplest. We're going to say y, velocity y2 equals velocity, velocity final in the y equals velocity initial in the y plus acceleration time. And if I plug these in, I get negative 6.0 equals positive 6.0 minus 9.81 time. And then I should be able to figure out that time value. And if we do this, we take 12 and we divide it by 9.81. The negatives should cancel so that you get a positive value for time, which they do to double check your work. 1.22 seconds. 1.22 seconds. That will be the time in the air. Right? Now, that time in the air by the way, is going to be affected by the angle in which you use, right? If I use higher angles, I'm going to launch it more straight up into the air. I would expect that at higher angles, I would have more time in the air. But if I have more time in the air and my angle's really high, lots of wide launching velocity, a lot of height, but I'm not going to get a lot of X direction, am I? Because if I have a higher angle, my Y component gets larger from the launch, but my X component gets shorter. So yeah, I'll have a lot of time in the air, but if that X component is significantly smaller, it's not going to go much range. Whereas if I launch it at a low angle, I'll have lots of X speed. Sure, lots of X speed. So I'd expect it to go really fast. But if I don't have much Y information, I'm not going to have much time in the air. And if I don't have much time in the air, even though I'm going really fast in the Y, if I don't have a lot of hang time, I still might hit the ground relatively short. There is a perfect balance of X and Y components when you launch. It's going to give you the maximum range and maximum distance, and that would be 45 degrees. Because 45 degrees splits that 90-degree angle right in half, and at 45 degrees, it's not the maximum Y velocity, no. It's not the maximum X velocity, no. But it is the perfect balance of X and Y initial launch velocities to get you the furthest, and therefore also the longest amount of time. No, wrong, back up. I misspeak. I misspoke. The 45-degree angle will get you the greatest range because it's the perfect balance between the velocities and the time in the air to get you that range. For the greatest hang time, it's actually going to be greater than 45 degrees. So be careful on that. Matter of fact, the greatest hang time is straight up. Goes straight up and straight down because all that velocity goes, assuming the overall velocity remains the same, all that velocity goes into launching straight up. You won't get any range, but you get maximum hang time. So, all right, back to this discussion. So now that I know in this particular case, it spends 1.22 seconds in the air, I can use that time, because these motions are happening at the same time, to find out my range. So if I take that and I put it into my, and remember in the X direction you're only allowed to use Vx equals delta X over t. No accelerations in the X direction. No acceleration formulas at all. And so we're going to have 8.0 equals delta X times 1.22. Delta X equals, and we got to multiply that out. About 1.5 meters, 1.5 meters. No, that's not right. That's not right at all. That is a mistake in my calculator. Hold on. So 1.22 times 8. Wow. 9.76 meters. All right. So I'm going to take a little break after this, and we're going to go into another part of the problem. I'm going to clean this up, and we'll keep this going.